Bir. Hello everyone and welcome to our presentation. Our project is titled as Embryo Viability Classification with Deep Learning, and this study was carried out as part of the World Championship 2023 Computer Vision track using biomedical image data. And we have a team of three undergraduate students from the Electronic Engineering 406 course. And I am Suat, and my teammates are Abdulkadir and Berkay. In the next few minutes, we will walk you through our approach to solving an important medical imaging problem using state-of-the-art deep learning techniques.
The problem we are addressing in this project lies within the field of vitro fertilization or IVF. In IVF procedures, selecting the most viable embryo is critical to increasing the chance of the successful pregnancy. Currently, this selection is done manually by embryologists based on visual inspection of the microscopic images. However, this approach is time-consuming, subjective, and can vary between clinics. Our motivation is to develop an automated, accurate, and consistent deep learning-based system to assist in embryo selection. A reliable AI system couldn't only reduce workload, but also improve success rate by offering objective recommendations.
To solve this problem, we built a deep learning pipeline based on transfer learning using pre-trained convolutional neural network. Specifically, we selected three widely used architectures: MobileNet V3 large for lightweight efficiency, EfficientNet B0 for balanced performance, and DenseNet 121 for deep feature extraction. We reused the convolutional layers from these models, all pre-trained on ImageNet, and added custom layers for binary classification. Uh, to enhance generalization and reduce overfitting, we applied data augmentation techniques such as rotation, flipping, zoom, and brightness adjustment. The final output layer uses a sigmoid activation, which allows the model to predict the probability of an embryo being good or not good.
And here we present a step-by-step overview of our complete pipeline. First, we load the datasets, which includes high-resolution embryo images along with their binary labels indicating viability. Next, in the pre-processing state, we resize each image to 224 by 224 pixels and normalize the pixel values and apply augmentation to artificially expand the datasets. Then we initialize our pre-trained models, MobileNet V3 large, EfficientNet 1, EfficientNet 00, and DenseNet 121 without their classification heads. We attach custom fully connected layers and compile the models with a binary cross entropy loss. And during training, we use techniques such as class weighting, early stopping, and learning rates schedule to improve convergence and prevent overfitting. After that, we evaluate each model using a validation set and select the best performing one. Finally, we generate predictions on the test set and export the results as submission files for the Kaggle leaderboard.
The dataset used in this project provided by the competition organizers on Kaggle consists of approximately 1,000 high-resolution microscopic images of human embryos. Take two deployment states, day 3 and day 5. Each image is labeled as either good or not good based on the morphologic criteria defined by the medical experts. For training and evaluation, we performed an 80 to 20 strip field split to preserve class balance across the both sets. In terms of metric, we evaluate our model using accuracy, precision, recall, and F1 score. Uh, we also analyze and confusion matrix to understand class-wise performance and detect any bias.
Our first model, MobileNet V3 Large, was chosen due to its lightweight architecture and efficient inference speed. During training, the model achieved the training accuracy of approximately 52% and a validation accuracy of 68%. The validation loss stabilized at 0.77, and overall performance indicate that the model was able to extract some meaningful features despite its smaller capacity. While not the top performer, MobileNet V3 Large show low overfitting risk and acceptable generalization, making it a solid baseline for comparison. However, the accuracy plateau suggests limited learning capacity for more complex biomedical features. Further tuning or deeper variants might improve its potential.
And let's continue with the EfficientNet. EfficientNet was expected to offer a good trade-off between model complexity and feature extraction. In our experiments, it reached a training accuracy of approximately 61%, but its validation accuracy was lower, around 53%. With a validation loss of 0.82, the model exhibited some instability during training, suggesting a medium risk of overfitting, and probably it's because low data sets. And also efficient nets struggle to generalize well in our setup. Its common scaling design could still prove beneficial with hypermeter optimization or fine-tuning of base layers. And this model remains of promising candidate, especially for resource constrained environments if its performance can be improved.
DenseNet one-to-one outperformed to other two models in nearly every aspect. It reached a triangle accuracy of 73% and validation accuracy of 81%, the highest among all the candidates. Moreover, its validation loss was the lowest at 0.42, and there were no sign of the overfitting throughout the training process. The model stands connectivity allowed efficient feature propagation and reuse, which provide advantages in the classifying subtle morphological patterns. DenseNet one-to-one was both accurate and stable, making it most reliable model in our embryo vehicle classification task.
This table summarizes the key performance metrics of all three models. As shown, DenseNet one-to-one achieved the best validation accuracy at 81%, with minimal loss and strong generalization. MobileNet V3 Large, while limited in feature depth, reached a respectable 68% validation accuracy, making it suitable for lightweight applications. And EfficientNet B0 performed moderately with 53% validation accuracy and medium overfitting risk. These results suggest the DenseNet one-to-one offers the best balance between depth, learning efficiency, and robust nets, while MobileNet V3 Large remains a good fallback for low resource deployments.
And in this slide, we present our final performance in the competition. Our submission achieved a public leaderboard score of 0.73, which places us at rank 15 out of all teams based on the public evaluation sets. However, since we submitted our final predictions after the competition deadline, our team doesn't appear in the official leaderboards. We have already contacted Kaggle via email, requested that our score be added to the rankings due to academic context of our project. Despite this, we are proud of our results, which proves that our model performed competitively among top teams, especially considering the limited data set and the complexity of classification tasks.
In conclusion, our project demonstrates that deep learning, particularly transfer learning, is a promising solution for automated embryo viability classification. Among three architectures we tested, that DesNet one-to-one clearly outperformed to the others, achieving 81% validation accuracy with a low validation loss of 0.42 and no sign of overfitting.
Using class weighting, data augmentation, and early stopping helped us control generalization and training stability. Despite challenges such as limited data, we were able to achieve a public leaderboard score of 0.73, which would place us to 15 among global teams in the Kaggle competition. Although our submission was made after deadline and doesn't appear in the official leaderboard, our results demonstrate strong competitive performance. For future work, we plan to explore model ensembling to combine strengths of multiple architectures and apply explainability tools such as GradCam to better understand decision making. And most importantly, extend the dataset to further improve robustness and clinical uh, appl- application.
And lastly, thank you very much for your time and attention. This project has been a valuable opportunity for us to explore real-world biomedical challenges using deep learning. We hope our work demonstrates how AI can contribute to clinical decision making and improve healthcare outcomes, especially in sensitive areas like IVF. And now we are going to continue with the program codes. And my teammates Berkay will continue with the code section.
We ensured the latest version of NumPy, ChatBoost, and Optuna are installed by the first uninstalling and reinstalling them.
And we import libraries for data handling, preprocessing, modeling, visualizations, and image processing.
And after that, we extract the zipped dataset and load the train and test metadata into pandas data frames.
Uh, this code selects and loads 10 images from each class, class 0 and class 1, then visualize these images side by side in the grid layout. Overlaps are prevented by leaving appropriate space between the images.
And after that, this code filters the image according to types D3 and D5, which is day 3 and day 5, and selects and loads 10 images from each classes, class 1 and class 0. And after that, these images are then visualized in a grid layout with four rows, D3 class 0, D3 class 1, D5 class 0, and D5 class 1, and num samples columns.
This code applies the augmentation ImageNet normalization to prepare the image data for training the creates data generators by splitting two dataset into training and validation sets.
This code checks the distribution of the labels in the training and validation sets. They visualize a set of images from the training set and their labels. The images are displayed in the grid layout and unused space are hidden.
And after that, this code checks if the labels in both the data frame and the one received from the generator are in one-hot encoded format and prints the results.
And after that, this code trains MobileNet V3 large efficient net B0 and DenseNet one-to-one models and compares their performance and validation set. It includes determining the optimal threshold, metric calculation, visualization, and performance table generation. These parts are results.
And then prediction and submission. By making prediction on the test dataset, just CSV files on the class distribution and the prediction results were created for each model. In addition, the class distribution were summarized in the table.
Code part, that's it. Thank you for your listening.
Thanks for watching and listening us. If you have any questions, leave it in the comments.